The skip connection is not a trick. It is one of the reasons deep models train at all. This is the workflow you'll know how to run when we're done, which trains a deep model with residual connections and reports accuracy with a clear reason about preserved gradients. I'm Professor Pi, teaching AI foundations with simple Python. Deep networks are powerful, but they hit a practical wall when they get very deep. Gradients flowing back to the earliest layers can vanish or explode. That makes the first layers learn slowly or not at all. In real workflows, this matters when you want a model with many layers to capture complex features from images or long time series. Residual connections, or skip connections, let the gradient travel a shorter route back through the network. That preserves learning signal and makes very deep models trainable. Intuitively, a residual connection is just adding the input of a block to its output. That sounds small, but that add gives the optimizer a highway for gradients. Imagine you stack many blocks. Without skips, the signal shrinks as it passes through each non-linearity. With skips, an identity path preserves magnitude. Strengths are stability and deeper capacity. Weaknesses include architectural overhead and potential need to scale the added branch in very deep setups. We will build a set of small experiments in PyTorch to see this effect. First, we measure gradients in a plain stack. Then we add a shortcut and compare gradient sizes. Next, we test many stacked layers to watch activation spread. Then we tune the residual scale. Finally, we train a tiny residual MLP on a toy regression target so you see training behavior. The code is short, and the ideas carry to bigger models. Now we run a simple plane network and inspect the first layer gradient. This snippet computes a deep plane network's first layer gradient size. We set a fixed C in PyTorch to make the random tensors repeatable. Then create a toy batch X and 3 weight matrices W1, W2, and W3 that require gradients. The forward pass chains torch.mm and torch.relu, which mimics stacking linear layers with relu. We compute a simple mean-squared output loss and call loss.backward to let PyTorch AutoGrad populate gradients. Finally, we measure the gradient magnitude at the first layer using W1 grad norm. Increasing depth without shortcuts often shrinks upstream gradients. The printed gradient norm shows how much learning signal reaches the earliest layer. Next, we add a residual shortcut and see how gradients change. This example adds a residual shortcut and measures the new gradient. We create 2 new trainable matrices, A1 and A2. Run the residual branch R through torch.mm and torch.relu. Then add the input X to form Y-res using the same mean-squared loss. Loss.res.backward triggers PyTorch AutoGrad to compute gradients for A1 and A2. We read the first branch's gradient size with A1 grad.norm, which reflects how easily learning signals flow back. The addition Y-res equals R plus X creates an identity path that preserves gradient flow to earlier computations. If you deepen R with more layers, the shortcut becomes even more important for keeping gradients healthy. A larger norm here indicates improved flow. Now we scale that idea up and compare many layers with and without residuals. This code compares signal preservation across many layers with and without residuals. We first build a plain stack by iterating over PS, applying torch.mm and torch.relu repeatedly, then compute its activation spread using plane.std. Next, we create 2-layer residual blocks with RS. For each pair, we make a small transform B and add it to the running activation before another relu. We again measure the spread using res.steed. Activation standard deviation is a simple proxy for whether signals vanish or blow up as depth grows. If you increase depth, the plane path spread often collapses while the residual path stays healthier. The printed STDs show that residuals keep signals more stable. Next, we test scaling the residual branch to control activation variance. This snippet tunes residual scaling to stabilize activations. Reusing the weights RS, we run the residual stack twice, once with a unit scale and once with a smaller 0.2 factor on the residual branch. Each forward uses torch.mm and torch.relu, then multiplies the branch output before adding it to the shortcut. We measure activation spread with steed, producing S1 for the unscaled version and S2 for the scaled one. Lower scaling shrinks variance, making very deep models easier to train by preventing exploding activations. If you increase the scale, variance grows and may destabilize training. The printed STDs confirm that smaller scaling tightens the distribution. Finally, we train a tiny residual MLP on a toy target and watch learning happen. This example trains a tiny residual MLP on a toy target with PyTorch. Two matrices, F0 and F1, form one residual block. Out W maps features to a scalar. We use torch.optim.sgd to optimize these parameters toward the target T, a simple mix of sine and a linear term from the input X. Each step builds C with a residual update using torch.mm and torch.relu, computes predictions y-hat, and applies mean squared error before calling backward and step. Reducing the learning rate slows convergence, but can improve stability. Increasing iterations typically lowers the loss further. The printed loss shows a trained residual model reaching a small error. In a real project, this tiny residual block maps to stacks inside larger models. The same pattern applies whether you use convolutional layers or linear layers. Residual connections keep gradients alive and let you safely add depth when you need more representational power. Recap. What it is: a shortcut that adds input to a block output so gradients can flow. When to use it: whenever depth hurts training or you need extra capacity. One caveat: residuals help, but you may still need careful scaling and learning rate tuning for very deep nets. Next step: try scaling the residual branch and training longer, or increase the number of blocks and measure activation STD and gradient norms to find a stable configuration. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.